Hey folks, for this lecture, I want to talk about aliasing and Fourier series. But before I talk about aliasing and the issues with that, I want to talk about Fourier series in general. And so Fourier series, what Fourier series is talking about is sort of the phenomena that any signal or any periodic function can be decomposed into a sum of sine waves. And so a lot of you guys in the last video, you used this program called Decibel X. And what this program does is it tells you your decibels down here, and there's a number down here. And so if I be quiet, that number is like 59, 60. And as I talk, and if I talk really loud into the microphone, I can get it up to like 104 decibels. But what's interesting, and no one really discussed this in their video, was that this here is actually showing you a frequency spectrum of my voice. And so the pink line is sort of like a maximum value over the frequency range, and then the yellow is like instantaneous. And so what's neat is if I just like do like a one tone voice, like if I do something like boo, you'll see the yellow line is pretty constant because I'm doing a constant tone. Now, if you notice in that voice, like when I do a boo sound, it's like it's kind of raspy. There's like a lot of like frequencies associated with that. If I do a higher pitched frequency, something like this, you look right there, you can actually see that there's a spike in the data. And the reason why there's a spike in the data is because this is called a fast Fourier transform. What it's telling you is that the frequency content of my voice has a spike at that frequency. It's saying that if you take my audio waveform from my voice and decompose it into frequencies, that spike in data, at that frequency, there is a large magnitude. And so what I can do in this next audio is I'll do that high frequency noise, and I'll change my pitch and watch that peak shift over from the, I guess, I don't care if it's left or right, but it's going to shift. So here we go. And eventually my vocal cords can't get a high enough frequency, but it'll actually tell you what that peak frequency is. Okay? So I wanted to show you that in Decibel X. And so now what I'm going to do is I'm actually going to kind of show you how some of this works. So I'm going to bring this up here. This is terrible filming, but hey. So I'm going to go to the Google, and I'm going to show you a couple of these things. So for one thing is that you can take, here's an example of a square wave, and what they do is they show the first fundamental waveform. And so this is sort of like the real and imaginary complex plane as it's oscillating through. And what they do is they add a waveform that has a higher frequency, smaller magnitude. And if you look, the frequency is slowly starting to get flatter and flatter. And so they keep adding all of these sine waves. And this is a super trippy video. I highly recommend watching this full screen on your TV with all the lights off. It's a really, really cool video. But anyway, eventually, you get to the very end where you add all of these sine waves and you get something that looks kind of like a square wave. And what you can do is you on Wikipedia, you can actually see they've sort of animated this square wave here. And what they've done is they've actually computed the Fourier transform for this. So they're saying that x of t is equal to 4 over pi, k equals 1 to infinity of this summation. And this summation is actually pretty simple to code. I've actually coded this example. And so I made a naught 2.5 to shift it up. But I've done, for some reason I have a 5 here and not a 4. Is this is a square wave, isn't it? A Fourier example? I'm going to hit go on here. Yeah, there we go. There it is animating. Oh, okay, I think the 5 is just a scale factor to get me up to 5. That's all that is. So anyway, so this summation here is coded up in this Python code, and all of this is on my GitHub. You can read the extension, so my Python Git. And so if you look at this, I'm doing a length space from 0 to 5 seconds, and I've got my fundamental frequency. I just have it 2 pi omega naught. This is just a scale factor of 2.5, and then I have a vector of zeros, it's first a vector of zeros, and I add 2.5 to it. And then what I do is I run through n from n to 100. And in this case, this is k, and over here I'm using n. And so I basically compute the b coefficients that are multiplied by this sine wave here. And so this is kind of this summation here, and I run through this and I plot it. So if I just go through the first sine wave here, let's see, did it come up? Oh, I have to go to 2, sorry. This should just plot just the first sine wave. So if you remember in that YouTube video, this is sort of the first sine wave here, okay? Then if I go and I say, okay, go plot 2 waves, all right? Now what it's going to do is it's going to, oh, you have to do odd, I forgot. So it's 4. You have to do an odd number. So those are the first 2, okay? And then if I do, say, the first 3, I'd have to go to 4, 5, 6. And so now it's going to plot the first 3. You can kind of see it's getting closer and closer to a waveform. Now, the computation of this square wave here, so the square wave itself is not necessarily computed. It's the Fourier analysis of the square wave. And then, by the way, that Decibel X function that I showed you showed me the frequency content of my voice. This picture here is the frequency content of a square wave. And so what it's showing you is spikes, and it's not like the voice of a human, right? So when I talk, I speak in all frequencies, and I have spikes depending on where I talk. But this pure square wave has specific spikes that are all offset by a certain amount, because these are fundamental harmonics of that square wave. If I kind of lost my train of thought here. So I guess what I was trying to, now I remember, what I was trying to get at was, how do you actually compute this waveform here, right? Where did this equation come from? Well, if you look in your textbook, here is the sort of decomposition of any waveform. So what they're saying is like, if you have any waveform like this, it can be anything, you can decompose it to look like this: A naught, A1, A2, all so on and so forth. And so you basically have a mean value, and then coefficients for cosine, and then coefficients for sine. And these are the integrals here. A naught is this, and then AN is this, and BN is this. And so you can actually numerically compute these. You can compute these analytically by hand too. And so computing these things by hand is kind of tough, but most of the time people just implement Fourier transforms. And so I've actually written these integrals here. So I have my B coefficients. It looks like I have 2 B coefficients here. It looks like I'm just doing a B10 and a B15. And basically it's just a loop on sampling of this waveform that I created. So I created this waveform here as an example. Here's an actual waveform where it's 2 times sine 2 pi 10. So that means it's got 2 waves in it, one at 10 hertz and then one at 15 hertz. And these 2 frequencies are then run through. I say I'm going to sample at a certain frequency and run through this. And again, I don't want to get into aliasing right now, so I'm just going to kind of run through these loops. And if I compute this, you'll see that this is my waveform, and then the red dots are my sampled points. And if you look at the magnitude, so this is 10 hertz, so B10, the coefficient of 10 hertz, is 2, which makes sense. And then B15, which is the coefficient at 15, is 1, right? That's the magnitude. So the magnitude of this coefficient is 1, and the magnitude of this coefficient is 10. And so again, you're looking at this sine wave here. What you're looking at is 2 sine waves put together. And then when you run a Fourier transform, what you're looking at is the magnitude of that sine wave at a specific frequency. Okay? And I've gone a step further on this, and I've actually written a fast Fourier transform here. So this is a fast Fourier transform, and what it does is it loops through all of the frequencies, and it does a Riemann sum to compute the cosine coefficients and the sine coefficients. And what I'm actually going to run this in command line because, I just closed it. Of course I did. I'm going to run this in command line just because it's easier for me to deal with it. And so I've got a lot of stuff in here, and I've got the code I'm looking for is record my voice. And so I think the way record my voice works is it says let's see, the length of time to record is 2, and then it's going to play it back, and then it's going to run the FFT. So what I want to do is I want to do / record my voice 2 for 2 seconds, and then I'm going to do 1 and 1 to record it, to play it back and run the FFT. I'm going to have to unplug my my headphones here, so my mic is going to be a little bit different. But what I'm going to do is I'm going to hold up Decibel X, and I'm going to make that one sound. Boo! Okay, according to the Decibel X, that was a 420 hertz sound wave. Okay, so I'm going to record my voice now, and 2 and 1 and 1. And what I'm going to do is I'm going to unplug my headphones. I'm going to hit enter. I'm going to attempt to make the same sound I just did, and then my code is going to run through and generate the exact same thing. So here we go. Okay, so there it is, playing back. And then there, I'm going to plug in my headphones again. Hopefully I don't have to do that again. And now what it's doing is it's running the fast Fourier transform. This is very, very unoptimized code. It is running through 2,000 frequencies, and it's computing the magnitude of the sound bite that I just sent to the computer and determining what the magnitude of each one of those frequencies are. So hopefully we will see a spike at 420 hertz. I could have a bug in my code. I could have talked differently. It's hard to say. So let's see. Okay, so we have a couple things here. So let's look at this. This is my sound bite. If I were to export this to a WAV file, this would be the sound bite. Okay, it's pretty good. There's a little bit of noise here, right, in this thing here. But for the most part, I feel like I did pretty good, creating a constant hertz signal. It looks like the amplitude is changing a little bit, but I did pretty good. So then what happens is that the Fourier transform, what it tries to do is it tries to match the signal. And if you look at that, the recreated waveform from that Fourier transform perfectly matches my original waveform. And again, it's because it's a pretty good sine wave, right? So then if I take the coefficients and I plot the coefficients, here are my coefficients. So it looks like right here, look at that, 422 hertz. So it means my code is, I wouldn't say just as good as Decibel X, because Decibel X is running in real time and my code took forever. But there is a spike in data right here. Now, if you notice, the spike is not perfect. There's some what's called leakage here. You're not going to get a perfect spike. You're going to get a little bit of leakage. That's a consequence of me talking. That's a consequence of numerical precision and things like that. It looks like there's also a spike over here. I'm pretty sure this is just a fundamental harmonic at 840. And it is, yeah, that's just a harmonic at 840. So it's hard to say if my voice was actually producing an 840 hertz signal. It was more than likely producing this signal, and this is just a harmonic picked up by the numerical precision. Okay. So what else do I want to show you here? So I showed you this Fourier example. I showed you this. Did I show you this? This was the video of the square wave. This here was the showing you the coefficients. So basically, like if you're given this as a homework problem, and I say plot magnitude as a function of frequency, this problem is really easy because the magnitude is 2 and 1, and the frequencies are 10 and 15. Now remember, this whole term is radians per second, 2 pi f, and then this here, this 15 is f in hertz. Okay, so just make sure you keep that in mind. So this aliasing example here, I'm going to show that in the next video. But I'm pretty sure that was what I wanted to talk about Fourier series and how it works. And so, oh yeah, I wanted to do this piano note. So what I wanted to do was talk about pianos. Like pianos aren't perfect, right? Just because pianos are kind of cool. Yeah, okay, so I heard it in my headphones. So I'm going to, let's see, I'm going to put this over here. I'm going to put this over here. I'm going to go back, GitLab, Python, sound, and I'm going to do /record my voice 211. Except this time I'm not going to record my voice, so I'm going to shoot. How do I want to do this? I'm going to do 4 seconds just to give me enough time. I'm going to unplug, hit enter, and then click my mouse to hit play. So here we go. Unplug, enter, mouse. Okay, so there was a little hiccup. There was a little hiccup at the beginning, but I'm hoping it grabbed it. So according to this wiki, middle C is 261.63. So if we did that right, was that middle C? Yeah, it said it was middle C. So if we're lucky, that little hiccup that I did at the beginning where I hit play twice, hopefully it'll grab 261. And you actually look at this, you can actually see that, you know, the A note on your piano is 440, and you can actually like march down the piano, and you can actually see that you can see the actual frequencies of it. Guitars are the same thing. You play guitar, they have they have frequencies that they're supposed to be tuned to, so your guitar sounds nice. All right, let's see. We're at 1,300 out of 2,000. We'll be there in momentarily. Computer's probably going to freak out on me here. And there we go. Okay, so there was, I think it tried. There was this weird hiccup at the beginning, and it couldn't do it. What did it grab? I mean, it did grab. It looks like there's 2 spikes. That's probably a harmonic. Let's see what this is. Yeah, I mean, that is. I'm not going to do this again because I don't want to waste your time. But it did grab 260, so it at least did okay. I think that little hiccup at the beginning, like you can see, the recreated waveform is just terrible. Had I not hit play twice, it probably would have been okay. But there you go. So there's Fourier series. So again, the objectives of this lecture were to show you that, you know, any sound bite, piano, guitar, your voice, any periodic function can be decomposed into a sum of sine waves. And what digital signal process engineers try to do is they try to plot magnitude on the y-axis and frequency on the x-axis. And what they're trying to do is they're trying to figure out what is that fundamental frequency that I'm trying to pick up. Okay, and then in the following video, in the companion video on this, I'm going to talk about how if you know what the fundamental frequency is of your sampling input, you need to use the Nyquist criteria to determine what frequency to sample at. And then that's where aliasing comes in. So I'll post a video after this on aliasing. All right, have a nice day.